right, so where there are derivatives, there are antiderivatives. So where a derivative takes a function, you take the derivative of it, and you magically get a what? Or an equation, maybe not a function, and you magically get an equation that now represents not values, but slopes or rates at which those values change, right? And you've seen that ever more clearly, even with what we just did. When I take a derivative, it doesn't just give me the rate at which y is changing, but y with respect to x, or area with respect to time, or volume with respect to height. It gives you the d dt of all of those variables, right? Well, what would happen if I gave you a derivative equation and asked you to go back to where you came from? Well, that's bound to have a rule or a process as well, right? So if there are rules like the power rule for going to a derivative, there's got to be rules to go back. And that process of going back is called an antiderivative. And what we normally use for an antiderivative, we represent it with this funny symbol called the integral. Okay? It's not an S. Okay? It really, in textbooks, sometimes it has a slant to it. Sometimes it looks very vertical looking. But it really is more like a vertical line with a little hook on the top and a little hook on the bottom. Okay? All right, I'm not grading you on that, but it'd be nice to have some kind of a decent looking integral sign. Yes?
Should Nolan be back
I didn't even know he left. I didn't know you walked out here.
Good you caught that.
Good man. I truly had no idea you were out there, because I normally tell people to go out, and I didn't. Nolan's back. Okay, so real quickly again, for you, when you're drawing an integral sign, which is what we call an antiderivative, and again, what we do with an integral is we go from a derivative back to the function that we began with. Now, let's be honest. Sometimes you begin with a function, and you're just finding the antiderivative of it. And I could take that function and integrate it again, and go back to one that was even before that, or whatever. So it's not always like there was one before. We're just integrating it. One way, take a derivative, you find a rate of change. You find an integral, and you're not finding slope. You're going from a slope equation or a random equation to something else. And we're going to talk about what that actually means later. You'd think you'd put the cart before the horse, but I actually want to know you how to do this, and I'm going to show you the mechanics of it before I show you what you're actually doing, okay, and why it is what it is. But I'll tell you, when you integrate some function with respect to x, from say from some x value to some other x value, and I'll just illustrate that real quickly here. Say this was a and this was b, and this was your function. When you integrate a function, what you're really finding is the area between that curve and that x-axis. So I can actually find all of that area right here. That's the area between the a and the b, right there. And the integral does that. And it actually does that through a mentality of summing little bitty skinny rectangles, okay, that have heights that are changing and little bitty tiny widths, infinite numbers of them, right? And we'll talk about that later, but right now all we're going to do is the mechanics of it. So you're going to learn the rules of how to do this. We're going to start basic today, and keep on going and adding a bunch of rules for about 3 or 4 days, and then I'm going to hit you with just practice, 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 okay? So I'm going to hand out this assignment sheet. I think you will see this. As you're looking at it, this should take us all the way through the rest of this week, and then the entire week when we get back. Okay? And there is a strong chance that we will not strong, there is a 100% chance that what we start after this, for those 3 or 4 days, will not be tested this semester. So all your exam will be based on just through this. All right? All right. So turn with me to that first page on integration in the book. No. No internet. Oh, I have ways. Come on, man. Killing me. Not good. That thing a little bit. Back. Okay. So uncool.
You shouldn't point your laptop. I would probably make it work.
What?
All
Alright, maybe I can say it like here.
Mr. Murray, do you know what the definition of insanity?
Touche.
I thought it was pudgy.
No, believe it or not, sometimes I keep clicking and it works. Okay, so we are somewhere near 71. Alright. Okay, so hopefully this is my most updated edition. So right here, introduction to integration. So remember, in integral, guys, don't always think, okay, why aren't these, a lot of people look at these and go, how come these aren't derivatives? Who says they aren't? Like when I take a derivative, I normally write it as f prime of x, right, or g prime of x, but I could have called it h of x. I could have called it m of x. I could have named it anything I want, right? It's still some other equation. It doesn't have to designate, like if I had an inverse function, sometimes I write f with a little -1 to indicate inverse, but sometimes I say, hey, h of x is the inverse function. So if I'm giving you these functions, right, and this is prior to the derivative, and I were to take the derivative of those top three, does everybody see that this is what I would get for the derivative of each of these? Right? And that's based on random derivative rules that you know or should know, or if you don't know, go back and make sure you learn them, because you're going to have a lot of trouble going back to whence you came if you don't even know how you got there. Are you with me? So if you don't know your derivative rules, and you might have noticed in your prior assignment sheet, it had an assignment after the test, which was to take that practice derivatives test. And that was for you to expose yourself and realize what you don't or don't know. So you're going to have to know those to be able to integrate. You can't go, oh, I forgot the quiz, he's not taking it, I'm not doing it. Do it. Because if you don't know those, you're not going to be able to get back, because you're going to be undoing your rules, basically. So it's really clear right here that I get these three, I think, these three derivatives, but it stands to reason if I can get from A to B, I should be able to go back from B to A. Okay? So if you really think about our power rule, which is what I'm going to focus on today, the power rule here was multiply the exponent by 3, and write that there, decrease the exponent by 1. Well, I'm going to go backwards then. So instead of decreasing the exponent by 1, I'm going to increase it by 1, and then take that new exponent and divide it into the power. Right here on this, I'm going to take that new exponent, which is 1, I'm going to increase it by 1, which gives me 2, and divide 2 into the 4, or the -4. On the 5, it's a little tricky. With a constant term, what would the x power be? It'd be like x to the 0 right here. So if 5x to the 0, the x wouldn't be there, but x to the 0 would mean increase that by 1, which gives you x to the first, and then divide by 1. Or you can just remember, if I ever have a constant, and I'm integrating a constant, just write 5x. If the constant's 5, just put an x on it. That's the easiest way to think through it without having to go, wait a minute, I'm going to put an x in there to the 0 power. But that's the power rule. Now, you might be looking at, what the heck is this c? Well, doesn't it, when you look at this, anytime I take an integral, anytime I take a derivative of a constant, what happens? It goes away. Well, how in the world then would I possibly know what to go back to if it's gone? I wouldn't. But I do know that there's something there. There's some constant. Might be 0, might be 2, might be -4. So because of that, I have to represent that constant that would have been there, because whether this is -4 or -40, -40,000, +500, I'm going to get a 0 when I take the derivative. So it stands to reason there's going to be some constant upon my return. Are y'all with me on that? And that's what this plus c stands for. So if this right here was a function, right? If this right here was the derivative, then if I integrated this, I would get back to the original function, and you can kind of see that with the exception of the c. Now, I mathematically haven't shown you any of the notation. So let me show you the notation on this. What you're really doing to integrate this 12, right here, this 12x cubed minus 4x plus 5, the way you show that notation is with that little integral sign I mentioned. So you take the function, you don't write f of x equals, and you put this little integral, and you put it in parentheses to show you're integrating all of it, and then you put a dx on the end. The dx is a little annoying. Last year my class did better than any year in the past by remembering you put dx. But right here there's a name for that, which I'll talk about down here at the bottom. But you got to remember, if the variable is a t, it's dt. If the variable is a w, it's dw. It's got to match the variable. If it doesn't match the variable, then there's work to do to make it match the variable. But you won't be given one where it doesn't match at all. Or if it doesn't match at the moment, you assume it's like a constant. You know, like if it was a pi, you know how a pi, you treat it like a constant when you take the derivative? So just like a 12, a 4, or 5, you would assume that it was a constant and treat it like that. But we're not getting into that, I don't see, in this year. So when you see an expression like that, that's when you pick up your derivative, your integral rules. So your antiderivative or your integration power rule says, increase the power by 1, take the new power, which is a 4, divide it into the coefficient, and that becomes your 3x to the 4th. Increase that power by 1, which gives you x squared, divide 2 into -4, negative 2x squared. Increase that power by 1, or just remember a constant, tack an x on it. That's what I do, but technically, that's a 5x to the 0. Increase it by 1 would give me x to the 1st, divide by 1 does nothing. So again, it's a whole lot easier when you integrate a constant. When you integrate a constant, don't think derivative, that doesn't become 0. Integrate it, puts an x on it, and then always don't forget your plus c. Not too bad? Now, you can do this whenever you have a power situation, okay, of x. Now, if I had something like a parentheses with a 2x plus 1, and then I was cubing it, you got some work to do. We'll talk about that tomorrow, okay? If I had 12x cubed times another function, you got some work to do. We'll talk about that tomorrow. So, in situations like this, where you have basically a term, add or subtract, a term, add or subtract, a term, you can integrate each one of those separately, and that's what I did. Track with me? Okay, now if you want to know why all this, if you're bothered by that dx, I tried to give you a little explanation here that might help a little bit. We know that dy dx is another way of saying f prime of x, right? What if I multiplied both sides by dx? That would show up there and it would cancel here, right? What if I integrated both sides, right? If I integrate both sides, then you have an integral of a derivative of blah. What do you think an integral of a derivative of blah is?
Blah.
Blah. And then you're left with this, okay? And then when you integrate a derivative, it should send you back to the what? Original function, plus some constant that I'm unaware of. So if that helps you understand maybe why the dx is there, but the real thinking on the dx, if we go back to that area example, dx is like a change in x, right? And if I were to think about a zillion little rectangles in there, like really skinny, almost like paper thin rectangles, right? If I could somehow find the area of all of those rectangles and add them together, it would represent the area of that curve. And the skinnier the rectangles, the better. So when I say skinny, I mean infinitely small, where the limit approaches 0. So you work a limit into this sum problem, and you do it to infinity, and that's what represents the integral. But since, and we'll talk about that later too, but since the expression's so ugly, and somebody noticed all these neat little tricks, heck, we're going to use these little rules that we have. We're going to do those just like you use your derivative rules. Your derivative rules are really limit problems, remember? Remember the definition of a derivative was a limit? How often have we been using limits to do derivatives? None, right? Same thing here. This is really a really ugly limit summation problem. But we're not going to worry about that. We're going to learn how to do these with some rules, and then when we have them all down, we're going to go home for Christmas, enjoy some food and some family, hopefully don't get sick, come back fresh, and then when we get back at some point, we're going to start talking about why this is what it is. And that is another branch of calculus, is really looking at the why. It almost seems like a waste of time because we're really going to walk through how to find areas using trapezoidal sums or sums of actual rectangles when it's not infinite. It seems silly to approximate that way, but anyway, we're going to do all that because AP tests you on it. Okay, so when you're looking at this right here, we call C the constant of integration. I normally just call it the constant right here. The G function that you're integrating is called the integrand. Okay, again, I usually say we're taking the integral of a function or an integral of an expression. I usually don't call it the integrand. I'm not super formal with that right there. And what you get, the function you go back to, we generally call the general solution. And we call it a general solution because of the C. If I ever determine what that C is, then we call it a specific or a unique or a particular solution. But a general solution will have that C on there. And again, this right here is the same thing as me saying the integral, this right here would be the same thing as me saying the integral of f prime of x dx gets me back to the original function plus some constant, right? But we don't always call it f prime. If we call it g, what we normally use is big G to show what we came back from. Like, all right, if this is the son, this is the father. Or if this is the daughter, this is the mother, right? It's where we came from. You with me? We capitalize it to be impressive. Okay, but that's usually relationship. So when you see lowercase g and uppercase G, that's a big deal. Don't think you can just interchange those and it's not a big deal. It's a big deal in calculus. So typically, if it's not already named, and you see a letter there, it's uppercase letter after you integrate. Are you with me? But if you see a derivative there, you're sending it back to whence it came. You tracking? Yeah, I heard George from somewhere. Self-Q. All right. So anyway, for whatever that's all worth, and we'll talk more about general solutions when we get to differential equations. And differential equations are really just more of this. You're taking a derivative equation and going back to a general solution. They're a little bit more complicated than this, but not much. But anyway, I wanted to show you these, and it's not just power rules they work for. Like, for instance, what's the derivative of tangent? The derivative of tangent of x. Secant squared of x. Well, guess what? What do you think the integral of secant squared of x is? Tangent x plus c. So there you go. If I'm integrating a 3 secant squared x, 3 isn't really part of that, so I'm going to just kind of, since it's times, I'm going to sneak the 3 out to the front. We're allowed to do that with multiplication of constants. I can never sneak a variable out, but I can pull out constants. So if that had been 3x out there, this becomes an entirely different problem. Right? You're not allowed to do that. But constants you can just swing out, and then look, if I recognize that the derivative of tangent gave me secant squared, then the integral of secant squared is going to get me back to tangent plus a constant, and then I swing the 3 over. Now, for those of you that are looking at my math here and going, I think you forgot to call that 3c. You're right, but what is c? What is 3c? Another constant. So some books initially will actually say things like, well, that's C1, and then when I multiply it through that, it gives me a different one. But then at some point, everybody goes, if I don't know it, I don't know it, right? It's just some constant. And universally, people just tend to get a little sloppier. But it is important to notice, when I have that 3 on the outside, if this integral was multiple parts, I do need to multiply that 3 into each part, if it's on the outside, okay? But the only reason why I don't reflect that there is because it's still just another constant. Track with me so far? Okay, do you remember that the derivative of 8 ln x, or specifically ln x, was 1 over x? Or actually, if you remember, it was put the x on the bottom, take the derivative of the x on the top, right? And then you just put the 8 over there and multiply together when you're done. Now you remember that. Well, that would mean the integral of 8 over x. If you don't like the constant, you can swing it out to the front, because we've been doing that, if it's multiplied or divided. Right? And then I have the integral of 1 over x. Well, if you know that the derivative of ln x is 1 over x, then the integral of 1 over x must bring you back to ln of x plus c. Are you with me? But you've got to know those. And if you don't know those, that becomes a problem. You have to know these derivative rules to be able to understand the integral rules. And then again, you multiply the 8 in, but again, if it's a constant, it's still a constant. Okay? So anyway, these are all examples. I think I talked about this 2 seconds ago. We generally say if we're integrating a little f, what we get back, like that original equation, we call it big F. If I'm integrating a little g, big G. But if I happen to know that that's an actual derivative, like if it's called f prime, then always integrating and a derivative basically cancels the derivative and sends you back to that original function, plus c. So, let me help you out with some of these and let's see what you can do. What if I'm integrating a 4x cubed? What does your power rule tell you?
X to the fourth,
So add 1 to the power
and then divide by the new power.
and divide 4 by the new power, which is a 4, leaving me a 1, and then don't forget the c. And if you ever want to check your math, take the derivative of this. What's the derivative of x to the 4th plus c? 4x cubed plus 0? Bam. All right, what about this next one? The integral of 5x. Well, it's x to the first, so increase the power by 1 gives me x squared. Divide that new power, which is a 2, into the 5. And then plus c. If you're not sure if you've done it right, take the derivative of that. What do you get? 10 halves x, which is 5x, plus 0. Bam! What about the next one? Integrated 9. 9x. And it's a whole lot easier just to remember when you integrate a constant, you get the constant times x than it is to think about that as 9x to the 0 and apply the rule. So I would encourage you to do that. Integrate a constant, 9, that constant times an x, plus a c. Are you with me? Now, with that in mind, that's my power rule. You would write this power rule like this. The integral of u to any n power du would be u to the what? N plus 1, n plus 1, plus c. That's a power rule. And I use u, and you'll see why tomorrow, because of this thing called u substitution. All right? And that's a big, massively big deal in APCALC. It's what we do tomorrow. So whether you're here at home, put on your thinking cap when you come in here and really make sure you do the homework. And I know I'll say that all year long, but man, you don't get u substitution down, and every year I get a handful of people. If you don't get u substitution down, your best case scenario is eking out a 3. If you get u substitution down, then the lid's off and you have the sky's the limit of how well you're going to do. Okay, but there's no way you're going to break a 3 if you don't get u substitution. It's not that bad, you just have to get it. Once you get it, you're like, oh, I get it. Okay, so that's the power rule, and it's on, you have a sheet, if you are flipping through your book, you'll run it at some point. There's all kinds of rules on there. I suggest you start learning them, but a lot of them you will notice when you look at them. Oh man, it is about there, isn't it? Oh, real quickly, let me show you a couple things to get you started on these. Number 4 looks pretty basic, but because those are regular old powers, right? But look at 5. What can I do on 5 to help me with the power rule? I can definitely take the 2 out, and then x to that becomes x to the negative 3 dx. Now you can apply your rule, right? What about this one? I can definitely take the 2 out if I want, but what about root x? X to the 1/2, now it's a power. Now just to help you with it, right? Add 1 gives you what? 3 halves, and then you do what? Divide by 3 halves, plus C. What is dividing by 3/2 the same as? Multiplying by 2/3. So you'd end up with 4/3 x to the 3/2 plus C. Are you seeing that? Hey, what about weird stuff like this when you're multiplying? Do you have a rule for that yet? You don't. You'd undo it, but I don't know how you're going to do that. How about FOIL it out first and then do it? Hey, what about something like this? Couldn't I? Yeah, guys, check this out. Couldn't I think of that as, if I have that over that, can't I go 3 minus 1 and it leaves you with the next squared?
That's great.
If I have this over this, can't I go 1/2, the 1/2 power, minus 1, and get that? Are you seeing it? Then I can apply my power rule. So on these, look for ways to apply the power rule, and bring me any questions tomorrow and we'll go through them. You have a great one. Absolutely. Anytime.